Let us look at insertion sort. For explaining insertion sort, I have taken an array of elements. So 5 elements are there. To reduce board work, I have just avoided indices, and even they are not required. Let us perform insertion sort. The very first thing is, I have 5 elements here. So we assume that this first element is already sorted. If there is only one element, then obviously it is sorted. So we assume that just the first element is sorted. Then the remaining elements are not sorted. So remaining elements will take out from an array and insert them on this side in a sorted list. So take out an element, insert this side. Take out an element, insert this side. So right now in an array, one element is sorted, 4 elements are not sorted. One element, that is 8, is sorted. So from the unsorted list, we'll take out an element and insert this side. Take out an element and insert this side. This is what the procedure is. So let us start the process. First step, I will insert 5. Insert 5. So for inserting 5, see, first element 8 is as it is. I am inserting 5. So the remaining elements as it is. Now the list will be extending to 2 elements. Now for inserting 5, check with this element. 8 is greater than 5. So shift it. Now check. There is nothing to check. So we have reached at the first place. So insert 5 at this place. So after inserting 5, the result is 5, then 8. Till here the list is sorted. Remaining 7, 3, 2, they are not yet sorted. So I have shown here how to insert 5, how to shift the element, and this is the result. So one element we have inserted. So this, let us call it as first pass. First pass. Then second pass. In second pass, let us insert 7. In the list, already 5 and 8 are sorted. Now we are trying to insert 7. So list will extend till here, and the remaining elements are this. These are not yet sorted. So 7 we are going to insert. So 7, take it outside. Now for inserting 7, start shifting the elements which are larger than 7 from right hand side. 8, it is greater. 5, no, it's not greater. So 7 should be inserted here. So the result after inserting 7 is 5, 7, 8 and 3, 2. Till 3 elements list is sorted. We will also analyze this one. See, how many elements were compared? Just one comparison. How many swaps? Means how much shifting? Only one element was shifted. So let us say one swap. Then in this second pass, how many elements were compared? In our example, only one element was compared. But at most how many? Both 8 and 5 can move, possible. If the number is smaller than 5, then both can move. So let us write down maximum comparisons and maximum swaps. So maximum comparisons are 2 comparisons and maximum swaps are 2 swap. Now we have to insert 2 more elements and sort 2 more elements. Let me continue with the rest of the elements. The resultant array, I will take it here. Now third pass, insert 3. So insert 3. So for inserting 3, take out 3 and the list size will be till here. This is a free space. Now start shifting the element. 8 is greater, shift it. 7 is greater, shift it. 3 is greater, shift it. Then 3 comes here. So after shifting and inserting 3, the list looks like this. Till here the list is sorted. 3, 5, 7, 8. Then this is 2. Then here, how many comparisons and how many swaps are done? 3. 3 comparisons and 3 swaps, right? These are maximum. Now one last element is remaining 2. So this is the fourth pass we will perform. Insert 2. We will insert 2. So in this array, when we insert 2, from this side we will take out 2 and the list size will be maximum now till the last element. Presently sorted elements are these, that is 3, 5, 7, 8. This is a free space. Now start comparing and shifting the elements. 8 is greater than 2, it will shift 7 also and 5 also and 3 also. Then 2 will come at this place. After shifting and copying the elements, Final array looks like this: 2, 3, 5, 7, 8. So that's it. This is sorted. We got a sorted array. So every time from right hand side we are taking out an element and inserting it on the left hand side. Left hand side list is always sorted. Now lastly, what are the number of comparisons? 1, 2, 3, 4. 4 comparisons we have done and maximum 4 swaps. Now let us do some analysis. So first of all, how many passes are required? Number of passes. Number of passes. 1, 2, 3, 4. 4 passes for 1, 2, 3, 4, 5 elements. 5 elements, 4 passes. Means 10 elements, 9 passes. So for n elements, how many passes? N minus 1 passes. N minus 1 passes required. Then how many comparisons? Number of comparisons. So find out number of comparisons. Let us check here. In the first pass, 1 comparison was done, and second pass 2 comparisons were done, third pass 3, and the fourth pass 4. So I'll add them. 1 comparison, 2 plus 3 plus 4. As there are 5 elements, 4 passes, so up to 4. N elements, n minus 1 passes, to up to n minus 1. So this is n into n minus 1 by 2. So this polynomial is of degree square, order of n square. As the number of comparisons are taken as the time complexity of algorithm, so time complexity of insertion sort is n square. Maximum time taken by insertion sort is n square. Now what about the swaps? Here 1 swap, maximum 2 swaps, right? Then 3, 4 swap and 4 swap. So for swaps also same as number of comparisons. So number of swaps for n elements, it will be 1 plus 2 plus 3 plus goes on to n minus 1, and this is n into n minus 1 by 2. So this is n square swaps. So maximum swaps are order of n square. So this is about comparisons and swaps. We have to check whether it is adaptive and stable or not, but before that I will tell you few important things about insertion sort. First thing, if I perform just 1 pass, what is the result? See, after the first pass I got 5 and 8. Is it useful anyway? Can I say that the first element will be smallest element? No, we cannot say that. That is not the smallest element. If suppose I have one more element, 9 here, can I say 8 is the largest element? No. So intermediate results, that is just 1 pass or 2 pass, will not give you any useful result in insertion sort. Like in bubble sort, if we perform 1 pass, we get the largest element, 2 passes, 2 largest element. But insertion sort, you will not get anything useful. Then second important thing about insertion sort. We have seen insertion in an array as well as insertion in a linked list. So in an array we have to shift the elements, but in a linked list we don't have to shift anything. So the benefit of insertion sort upon linked list is that you don't have to shift the elements. Without shifting you can insert. So insertion sort is more useful or more compatible with a linked list than array. Or I should say that insertion sort is designed for linked list. Yes, it is designed for linked list. So remember this point. For sorting linked list, insertion sort is better. Now next I will write on the algorithm for insertion sort. Then later we will analyze rest of the things.